Look at this creature. To our human eyes, bound to a single, static appearance, it seems to perform an act of pure magic. A shift from a vibrant green to a dull brown. A sudden burst of color. A fleeting moment of brilliance that seems to appear from nowhere and vanish just as quickly. The chameleon. The master of disguise, the living canvas, the ultimate illusionist of the animal kingdom. For centuries, we saw this as a trick, a simple biological parlor game played out on the skin of a creature. But what if we've been asking the wrong question? What if the chameleon's magic is not about what it hides, but about what it reveals? The question that echoes in the quiet moments of the night, a question that lingers beneath the surface of our reality, is not just, how does the chameleon change its color, but what is the true nature of its existence? Is it a simple act of survival, a biological quirk designed for camouflage? Or is it a profound statement, a language spoken in light and color, a secret so elegant and so logical it could redefine our understanding of identity itself? The answer, we find, is not in simple biology, but in the very physics of light, in a masterpiece of engineering that lies hidden beneath its skin, a secret that is not about hiding at all, but about a conversation with the universe. To understand the chameleon's defiance, we must first descend into its world, a world where the laws of physics operate on a different scale, a world of incredible, unseen power. For a long time, the scientific community believed they had the answer to the chameleon's secret. The old story told us about special cells called chromatophores. These cells, we thought, were like tiny sacks of paint, filled with different pigments like red, yellow, and brown. The theory was simple. To change color, the chameleon would simply expand or contract these sacs, spreading the pigment to show the desired color or bunching it up to hide it. A simple, elegant, and ultimately incorrect explanation. This theory failed to explain one critical part of the chameleon's trick: the sudden, dramatic shifts to vibrant blues, a color that no amount of pigment could ever truly produce. It couldn't account for the speed of the change, or the way the skin seemed to shimmer with an almost otherworldly light. It was a good story, but it was not the truth. The real secret, we now know, lies not in what the chameleon's skin contains, but in how it is built. The true architects of the chameleon's color change are not pigment-filled sacs, but a completely different type of cell called iridophores. These cells are located in a layer just beneath the chameleon's transparent outer skin. And within these iridophores lies the real magic, a complex network of tiny, light-reflecting nanocrystals. These crystals, made of guanine, are arranged in a highly ordered, geometric lattice. They are like an army of microscopic mirrors, positioned with perfect precision. But the chameleon's genius is not just in having these crystals. It is in its ability to manipulate them. By relaxing or tensing its skin, the chameleon can change the precise spacing between these tiny crystals. It is a biological equivalent of adjusting the focus on a camera lens. But instead of focusing an image, the chameleon is focusing light itself. This is the key to the chameleon's impossible power. It is not using pigment to color its skin. It is using physics to create color out of thin air. To truly grasp this concept, we must understand the difference between pigment color and structural color. Pigment color is what we see in a painted wall or a flower petal. It is the color of the material itself because it absorbs certain wavelengths of light and reflects others. Structural color, on the other hand, is what we see in a peacock's feather or a soap bubble. It is not caused by pigment, but by the way light waves are reflected and scattered by tiny, repeating structures. This is exactly what the chameleon does. When its skin is in a relaxed state, the nanocrystals are packed closely together. When light hits this lattice, the specific spacing of the crystals causes them to reflect only the blue wavelengths of light. This is why the chameleon's resting color is often a cool, calm green, which is a combination of the reflected blue light from the crystals and the yellow pigment in the layer below. But when the chameleon gets excited, angry, or wants to attract a mate, it tenses its skin. This physical action stretches the iridophore cells, increasing the distance between the nanocrystals. This change in spacing changes the wavelength of light that is reflected. The crystals begin to reflect the longer, warmer wavelengths like yellow, orange, and red. It is a biological prism, a living light show, a conversation with the world conducted through the very nature of light itself. The story does not end with a single layer of crystals. The chameleon's skin is a masterpiece of multi-layered design. Below the outer layer of iridophores, there is a second, deeper layer of iridophores. The crystals in this deeper layer are larger and less ordered, and they are responsible for reflecting the infrared light from the sun. This allows the chameleon to control its body temperature, a crucial function for a cold-blooded creature. By changing the spacing of these deeper crystals, the chameleon can either absorb more heat by turning dark or reflect it by turning light, a perfect example of its body being in a constant dialogue with its environment. But that's not all. Below the iridophores, the chameleon has yet another layer of cells, filled with the old, familiar pigments we thought were the whole story. These cells, called xanthophores and erythrophores, contain yellow and red pigments. These cells are essential because they provide the base colors. The beautiful green we see on a chameleon is not just from the iridophores. It is the result of the blue light reflected from the top layer of crystals passing through the yellow pigment in the layer below. And a vibrant orange is created by the red pigment combining with the yellow from another layer. The chameleon's skin, therefore, is a complex, living palette with different layers of cells working in perfect harmony, a symphony of light and color playing out on its body. The chameleon's color change is so much more than a trick for survival. It is a rich, complex language. Chameleons communicate their emotional state through color. An angry male will often display a rapid succession of vibrant, aggressive colors to warn a rival away. A female ready to mate will show a specific pattern of colors to signal her receptiveness. A fearful chameleon will instantly turn to a dark, nondescript color to appear submissive. The chameleon's skin is a living text, a silent conversation with its world. The chameleon's secret is no longer a biological curiosity. It has become a profound source of inspiration for human engineering. Scientists and engineers are studying the chameleon's iridophores to create new smart materials. Imagine a military uniform that could change color instantly to match its surroundings, or a car that could change its paint color with the press of a button. Companies are even developing flexible, color-changing display screens based on the same principles of structural color. The chameleon's skin, we discover, is a blueprint for a new generation of technology. The next time you see a chameleon, do not just see an animal. See a masterpiece of engineering. See a living, breathing testament to the fact that the most elegant solutions are often found in the most unexpected places. See a creature that understands the universe in a way we are only just beginning to comprehend. See the living, breathing proof that what seems like magic is in fact a beautifully logical reality.